Good day, everyone. My name is Manisha, and I'm here today with my team Dhananjani, Dimal, Tushan, and Nipune. Together, we are Group 13. We are excited to present our project, the Geospatial Analyzer. It's a WebGIS based platform designed to automatically monitoring mining rehabilitation using remote sensing. In simple terms, it's a web tool that uses satellite images to check how well mining areas are recovered. Now, you might be wondering, why is this need? Well, currently, monitoring the recovery of mines is mostly a manual process. This means people have to physically go out and inspect these large and remote areas. This old way of doing things have some big problems. First, it's slow and require a lot of efforts. Second, it can be inconsistent because one person's opinion might differ from another's. And finally, it's limited. You can't be everywhere at once and you can't check every offer. So the problem is that the current method is inefficient and doesn't give a complete picture. So the solving problems we create our WebGIS based automated monitoring system. Here how it works in nutshells. A user like someone from a mining company or an environmental board can simply type in the coordinates of the mine. Our system then automatically grabs recent satellite images of that locations. It runs a special analysis called NDVI, which basically measures how healthy and dense the vegetation is. This tells us if plants are growing back. Finally, the system generates a real-time progress report, show how the rehabilitation is going. The main goal is to make monitoring easier, faster, and more transparent for every involved, helping to ensure our environment is being stored and properly. To bring this to life, we built a GIS-based web application for the tech survey in the room. We developed it using IntelliJ, which is a powerful and efficient coding environment that helps us to manage our project smoothly. The front end, which is what the users sees and interact with, was developed using React to create a dynamic and user-friendly interface. And the backend, the bring that handle over the complex calculation and image analysis, was built using TypeScript. And with that, I will now hand over to Dhananjani, who will through the develop pacer and our analysis features. Thank you.
Thank you, Manisha. Hello, I'm Dhananjani. Going to walk you through the architecture of the geospatial analyzer, a full stack application built for environmental monitoring. It's designed to perform two key types of analysis: a local single E analysis on user uploaded satellite bands and a powerful multi-year time-lapse analysis using a cloud platform. The tech stack is a Python Flask backend for the heavy lifting and a React frontend for a dynamic, responsive user experience. Let's dive into the backend first. The Flask backend and analysis logic. Here in app.py, a Flask server handles all the core logic. I've set up two primary endpoints that power our analysis. First, we have the upload bands analysis endpoint. This is for our local processing. It takes a set of GeoTIFF files, specially bands 2 through 6, and a series of coordinates defining an area of interest. I'm using the raster library to open and read these satellite images. A crucial step here is aligning the bands, as they might have different resolutions. I reproject them to a common grid. Then, using NumPy, I calculate standard environmental indices like NDVI for vegetation or NDWI for water. The user-defined coordinates are converted into a polygon mask, and we apply it to get statistics like minimum, maximum, and average index values only for their specific study area. Finally, I use Matplotlib to generate a color-coded map of the results, save it as an image, and send its URL back to the frontend along with the stats. The React frontend and user experience. Now for the front end, it's a component-based React application built with TypeScript and styled with Tailwind CSS. The main entry point is the dashboard layout, which manages the overall structure, including our sidebar for navigation. The sidebar allows users to switch between different views like About, Settings, and our two main analysis tools. The analysis view component provides the interface for our single-year local analysis. It's a form where users can upload their band files and input coordinates for their study area. The time-lapse component is the interface for our Google Earth Engine feature. Here, users can input coordinates to define their study polygon, select a start and end year, and choose an index. Upon submission, it calls our backend API. The real highlight is how it presents the results. We get back the video URL from GE and embedded it directly. We also receive detailed yearly statistics, which I use to create an interactive trend chart with the recharts library and a detailed statistics table. This gives the user a rich, multifaceted view of environmental change over time. So that's a quick tour of the geospatial analyzer. By combining a local processing pipeline with Restorio for specific datasets and the massive scale cloud computing of Google Earth Engine, we've created a flexible and powerful tool for geospatial analysis. Thank you, and over to Dimal.
Thank you, Taranjani. Now I'll be demonstrating how our product actually works. Introducing Geospatial Analyzer, a smart and automated platform designed for monitoring, mine rehabilitation, and other environmental challenges using satellite data. As we can see in the first screen, the process begins with creating a user account. Here, we sign up as a new user by entering our basic details. Once the account is created, we can simply log in using our credentials to access the Geospatial Analyzer dashboard. After logging in, we are directed to the home page. This page provides a short introduction about the platform, highlighting its purpose, key features, and our visions and mission. It gives users a clear idea of how the system contributes to sustainable and landmine management. On the left side of the home page, we have a navigation pane. From here, we can easily select the type of analysis we want to perform, depending on the time period. Now, let's move to one of the main features, the Satellite Image Analyzer. This tool allows us to analyze the rehabilitation process of the selected mine site up to a specific date. To start, we first enter project name. Next, we select the year. Then we upload the required satellite image bands either from Landsat or Sentinel-2 captured for the area on the selected date. Then we need to select the analysis category. As you can see here in the drop-down menu, we can select either NDVI, NDWI, EVI or MNDWI depending on what we need to examine. For this demonstration, I'll proceed with NDVI analysis. After entering the site boundary and coordinates, we simply click the Run Analysis button. Within few seconds, the system generates a detailed NDVI analysis report. As you can see here, it displayed an NDVI map along with pixel-based NDVI values. The report also includes automatically generated comments and interpretations based on the analysis results, helping users to understand the land's current condition and rehabilitation progress. By following the same procedure, you can also generate same kind of reports for each index category separately. Okay, then let's move forward with the time-lapse analysis tool. Here, you can see that the process is quite similar to what we followed in the single year analysis. The main difference is that instead of selecting year, here we select a time period, for example, from one year to another, to analyze how the site has changed over time. Another key difference is that in this case, we won't need to manually upload any satellite image bands. Then, after we run analysis, within few seconds, the system generates several useful outputs. First, it produces a time-lapse video of the selected area showing the visible changes over the chosen period. Then it displays a trend graph that shows how the selected index, for example NDVI or NDWI, varies with time. It also provides a chart that clearly represents the index values across different years, helping to identify increasing or decreasing trends. If needed, we can even view an enlarged version of the time-lapse video for better clarity. This makes the time-lapse analysis tool a very powerful and efficient feature for observing long-term rehabilitation progress and environmental changes.
Thank you, Dimal. Here I would like to quickly go through the main positive implication of our project as shown in this slide. Our system support real-time monitoring, meaning we can see the latest change at the mine site as they happen through up-to-date satellite images. Automation is built in, so most tasks like data collection and analysis happen automatically, saving us a lot of manual report. This also being cost efficiency, since we don't have to visit the field as often, which save the both time and money. We make sure our results are highly accurate using advanced analysis. User accessibility is top priority. We have designed the platform so any permissible party, like regulatory authorities, mine operators, or other researchers can easily log and view the data. We value transparency, so all progress is open and visible, helping building public trust in mine rehabilitation monitoring process. Our system offers decision support with clear visuals and reports that help authorities and site managers to decide what to do next. It is also scalable, so as project grows, we can monitor more mines or even other regions without rebuilding the whole system. And finally, everything we do is aimed to environmental sustainability, encouraging responsible land recovery and green mining practices. As a summary, this platform modernized the mine rehabilitation monitoring, making more efficient, accurate, transparent and sustainable. Thank you. I will hand over to Nipuni to continue the next part.
Thank you, Dushan. We have a plan to further develop the system into a comprehensive land use monitoring platform. Beyond mine rehabilitation, its capabilities will be expanded to address broader environmental and land management applications, including deforestation monitoring, river meandering analysis, urbanization impact assessment, agricultural land use dynamics, and disaster impact mapping. For that purpose, the following system enhancements are proposed. Incorporate other remote sensing indicators such as soil adjusted vegetation index to assess water presence and soil conditions. Develop a mobile friendly interface for field officers to view data and upload site photos in real time. Combine data from multiple satellite sources to improve temporal and spatial resolution. Drone data integration allows the system to import UAV or drone-based imagery for high-resolution site validation. Use machine learning algorithms to automatically classify land cover types and detect rehabilitation or land use changes. Cloud-based data storage store analysis results in cloud servers for easy access, scalability, and long-time data management. Add a feedback module where users such as mine operators or GSMB officers can submit on-ground observations to verify results. Set up automated alerts for significant environmental changes or non-compliance detected in rehabilitation or other monitored sites. This slide summarizes all key resources that support the system design and development. Finally, I would like to thank all contributors, especially our supervisors, for their continuous guidance and support throughout this project. Thank you all for your attention.